All right. So my name is Uche, and I'm an MIT alum of 2022. Would anybody else want to introduce themselves? No? Yeah? All right. So today I'm going to go over ML and JAX. So we're... oh, okay. Hi, Joe. So today we're going to go over ML and JAX. So first I'm going to go over a primer of what ML is, what do we do at what at Gridspace do we do with ML, and then I'm going to go over JAX, which is the specific library that we use to do ML at Gridspace. So first, machine learning. What is machine learning? Machine learning is the realization of human-like action through learning by machines. So if we break that down, AI as a general field is the realization of human action or intelligence by machines. What we're interested in is specifically the subfield of ML where we learn how to do these things. So for learning, what that means is that we can take data and we can draw conclusions from it, and we can apply that to data that we maybe have never seen before. So for examples, we can take linear regression, and that would be trying to draw a line through points that we maybe don't exactly form, that we aren't given a line for, or clustering, where we are given many data points, and we're trying to group them together into overarching categories. And specifically for Gridspace, we're interested in NLP, which is applying and understanding linguistic knowledge in a human context. So that would be things like text-to-speech, speech parsing, which is just the inverse of that, and then emotional valence. When somebody's saying something, are they feeling happy, sad, angry? And dialogue acts is something like a greeting or something like a exclamation or a question. So specifically at Gridspace, we're interested in a subfield of machine learning, which is called deep learning. And the main star of the show would be the neuron. So deep learning basically posits that if we emulate how humans learn, we can make machines learn the same way. So first we have this model of a neuron, which is, we have the dendrites here, the nucleus over here, and we have axon with its terminal at the end. And basically, a little biology lesson would be the dendrites receive neurotransmitters from axons of other neurons, and those create a chemical electrical response in the nucleus, which then travels down the axon and then produces neurotransmitters over here at the axon terminals. So if we were to simplify that biology lesson, we can just say that we take a bunch of inputs, we do some operation to them, maybe with some value of weight, and then we produce outputs. So maybe one neuron may not be able to do all the things that we mentioned, like how do you draw a line with just one neuron? Like you only have an input and you have an output. But if we were to connect them together, then we'd have what we could call a neural network, which is exactly how humans have their own neurons connected to form the structure of themselves. So we have some inputs, we have layers of neurons, and then we have an output. So for a more human example would be if we're trying to recognize goose here, or an image, or what is a dog, we would want to see, we'd first have to receive an image, and then we'd put it through layers of our neurons that maybe will like recognize the contour of the ear or something like that, and then put it together, and then we output what are we looking at? So are we looking at a dog, a rabbit, a cat? What are we looking at? So there are many ways that we can put together these neurons, and some of those ways are we have a fully connected neural network, which if we look at this slide, this is a fully connected neural network where you just have neurons that go in one direction. So we go from input neuron to hidden layer neuron to output neuron, where we don't connect backwards. This is the most simplistic structure. Well, it is the most simplistic structure for a neural network. However, for certain problems, we can do better. So we have recurrent neural networks where we have feedback connections, where a neuron might not connect only to a neuron that is heading towards the output, but a neuron closer to the output might connect back to an earlier neuron. This allows us to encode temporal information in a way that feed-forward neural networks just can't. Then we also have convolutional neural networks, which can be represented in a fully connected neural network. However, what the fully connected neural network doesn't really encode in its structure that a convolutional neural network does is it encodes the properties of locality and independence. What temporal, in the case of signals, what temporal and spatial locality just mean is that related information is located together in time or in space. And then temporal spatial independence means that no matter where in the signal this information is, it does not change its meaning. So, for example, an image of a dog at the top left of this, at the top left of the slide, if I had an image of a dog here, would be the same as if I had an image of a dog here or here. And the pixels of that dog would be together in one place. Then we have GANs, we have generative adversarial networks, where instead of having something tell us a label, we have another network that tries to discriminate what value we've produced, what information that we've produced from a network. And our goal would be to get that discriminator to essentially misdiscriminate, to get it wrong. So an example would be if we're trying to generate images of faces, we would try to get a discriminator to take something that we took from noise and put it through a network to classify it as a face, even though it was from noise. And then finally, for most relevant to us as Gridspace, is a transformer, which encodes, which its most important feature is that it encodes attention, which is basically it can take an entire input and pick out certain parts of that input and mark them as relevant for a certain part of the input. So, for example, if we took the sentence, the boy runs down the street, runs might actually pay attention to what plurality the subject is, because its form depends on the subject, but not really the object in English. So when we're using neural networks, we have to go through multiple stages. So first we have to train the neural networks because we have just an architecture and we need to like specialize it for the question that we're trying to ask, what we're trying to learn. So we have, first we have a loss function, which we do have, this is where the difference between supervised deep learning and unsupervised deep learning comes out, where in supervised deep learning, the loss function is given to you. Essentially, you are given an answer for every data point, and the loss function is basically evaluating how close the answer that you've produced from your network is to the answer that you were given. But unsupervised learning would be taking the data and trying and having an answer from the data. So to give an example of a supervised learning, deep learning problem might be, given this context and this phrase of a sentence, continue the sentence to its end. And an unsupervised learning problem might be, given this context and given this sentence, we will mask one of the words. Give me what you think the word that we masked was. And the other part of training is that we have optimizers, which basically try to analyze the loss function and adjust the weights of the network such that we will get a better answer. The most basic optimizer is gradient descent, batch gradient descent. As we'll get in later, as I'll show the example, it has many caveats, and there are better optimizers out there. That's what I'm going to say about that. Then we have validation. This is a pretty important step because you might have multiple architectures of these neurons, because you might not know how many neurons to put in each hidden layer or how many hidden layers to have. A hidden layer is just a layer of neurons between the input neurons and the output neurons. So adjusting these parameters would be necessary is necessary to get the best results. And we have a production or testing set, which is data that you use to evaluate your network that was not trained on, that was not used to train that network. This basically is meant to avoid the problem of overfitting to your data. What overfitting means is that it is when you evaluate, when your network too closely resembles the training data that you were given. That is a problem generally because the goal of machine learning is to learn like a human, and generally humans can generalize. If a human looks at an image of a dog that they've never seen before, generally they do have some way of being able to identify that as a dog and not a mouse, for example. So generally we want to use a testing set to evaluate how well our neural network fits the question that we're trying to answer without looking too much at its training data. And then I'm just going to quickly go over word embeddings. Why do we use them? So word embedding, like the simplest word embedding would be a bag of words. If we have a set dictionary and we just one hot encode it, which is put a 1 in the vector if that word is present and a 0 if that word is not present. However, this does not, the main reason that we don't want to use this is that it does not encode relations between words, which is a central feature of language. It is the difference between a and dog, cat, mouse, door. So we generally want to encode these differences when we're using neural networks so that we can learn from these differences. And these are just two word embeddings that are relatively well known. We have word2vec and glove. So are there any questions on just this very quick run through of machine learning? Yes.
So would you say it's not overfit model having diverse training data for you, like different types of dogs would be more important, or constantly like just a large pool of different same dog?
I'd say having a diverse training set is more important if you're trying to because if you're taught that one breed of dog is what a dog is, you might if a human were to just be shown one breed of dog and they were told that was what a dog is, reasonably they might expect that if you were to look to another breed, they might not know what it is. So it is I believe it's much more important to have variety in your training set than it is to have amount. Yes.
What's the difference between
Oh, the difference between reinforcement and supervised learning? Unsupervised learning. Yes.
Oh. So just to say, when someone asks a question, if you could also repeat the question.
Oh, okay. Yeah. So what is the difference between reinforcement learning and unsupervised learning? From what I remember, reinforcement learning generally has a certain goal that it's trying to achieve, whereas unsupervised learning generally is more for trying to categorize things or miscategorize things in the case of GANs. So an example would be trying to win a game of chess. You might use reinforcement learning, whereas trying to generate a face that is of a person that does not exist might be more unsupervised learning problem. Are there any more questions? Yeah.
The way I often do it is if you do them on label dimension size from unsupervised and 0.
Yeah.
Reinforcement would be small.
Yeah.
Supervised and then generative model, very large dimensionality.
Okay, I'll just repeat that. So generally, unsupervised learning has 0 labels on the. There's no labels, and reinforcement has very few or 1, and then generative models have many labels. Yes.
Yeah, I just had a question. Like, if we have multiple categories or tables, can we use reinforcement learning to make our guesses better?
Okay, so if we have multiple categories, can we use reinforcement learning to make our guesses better?
Yeah, because it's like, again, a game of chess, we're kind of optimizing so that we can
Yeah.
make guesses better.
Yeah. Generally, for reinforcement learning, you have a goal, right? It's generally a set of states that if you achieve them, you win, or the goal is achieved, right? So if you have multiple categories to make guesses better, generally I believe that would fit more under trying to take something that's uncategorized, because you take something that you're not sure where the guess is and categorize it as one of these categories, right? So I believe that would be more unsupervised learning than reinforcement learning. Yeah. Any more questions? No? All right, so let's go to the second half of this lecture, which is on Python and JAX. So first, I'll just skim over. What is Python? So Python is a general purpose scripting language. And the main reason why that would be the main reason why that would be surprising in the context of ML is that generally we're trying to squeeze performance out of a machine when we're trying to learn. So why would we use a general purpose scripting language? So like, why not use C, right? Generally, the surprising bulk of what machine learning is trying to get data from one place and one form to another place and another form. And for that, the overhead of having to manage your memory and not having some niceties of scripting languages generally isn't worth the trade-off when you can make the scripting language faster. So the next question that you could ask is Python too slow? And that really depends on what you're doing. So if you're just trying to do the bulk of machine learning and trying to get data from one place in one form to another place in another form, not really, it's not too slow. But if you're trying to quickly train a model, or you're trying to get billions of points of data from one place to another, it might be a little slow. So to solve that, so like I just wrote, this is actual code that you can run, and it just does a basic dot product of 1,000 numbers. If we look at the basic Python, like just the Python implementation of this, you'll see that it takes 0.3 milliseconds. And as I'll mention later, we have Numpy and JAX here, which both take less than that. So maybe we don't want the actual operations of our neural network to be in just Python. But nobody ever does that. What they use is at least Numpy. So Numpy basically provides two things. It provides many efficient ways to manipulate data, and it provides a single data type in Python that can represent scalars, vectors, matrices, and more. What is that data type? It is a tensor. So we can consider a tensor to be a generalized matrix. Basically, a zero-dimensional tensor would be a scalar. A one-dimensional tensor would be a vector. I should use this. And a two-dimensional matrix, a two-dimensional tensor is a matrix, and then an n-dimensional matrix is a tensor. So if we call this data type in NumPy just an ND array, but it would be called a tensor. So then that comes now we get to the crux of this lecture, which is deep learning libraries. So we have ML libraries. We have scikit-learn that can answer general ML questions like linear regressions or clustering. But then we get to deep learning, which is what we're particularly interested in, which is the usage of artificial neurons to answer questions that used to take a human to answer. And basically in Python, we have three choices. We have PyTorch, we have TensorFlow, and we have JAX. And what we use at Gridspace is JAX. So that's what I'm going to talk about. So why JAX? So let's go over a little bit of history. So there was a lab at Harvard that was trying to make Python differentiable, just like pure Python functions, just make them differentiable so that you don't have to maybe you can use like loops and make them differentiable, right? Because if you've used NumPy, you know that like generally they tell you to avoid loops because They can't be vectorized because NumPy doesn't handle that. But at this lab, they're just trying to make it so that you could write whatever Python code within certain constraints and make it differentiable. And then there was another team at Google that was trying to do GPU processing of linear algebra code, which was to basically do what NumPy does, but do it on a GPU, which the difference between CPUs and GPUs become very relevant when you're trying to do deep learning, because if you have a billion different neurons, you do want to like process them in parallel rather than in sequence. And a CPU is specialized to process things in sequence, which is why it's problematic at a processor level. So JAX is just literally a combination of AutoGrad, this Harvard project, and XLA, this Google project that was done by Google. Essentially, Google brought the Harvard team to Google and made a super team, right? So it basically has differentiable Python on GPUs. So how does it do that? So first, we have immutable NumPy, which is a means to an end. So basically, it's just NumPy, but you cannot mutate in place. That means you can't just change what the value of a tensor is, leaving the same tensor in the same place that you placed it initially. And then the end would be AutoGrad, which is just basically you can differentiate Python functions that use this immutable NumPy. And it is meant to handle pure functions. So you'll ask me, what is a pure function? And I'll tell you that a pure function is a function without side effects. Then you'll ask me, well, Uche, what is a side effect? And a side effect is simply something that a function does that is not its return value. So, for example, if you were to print something to a console, the printing of something to a console is a side effect of the print function. Or if you were to mutate something, the mutation of a variable is a side effect of the function that is mutating that variable. So basically, with AutoGrad, you don't want to do that, which is why we have immutable NumPy, so that you can't do that and you can't shoot yourself in the foot. And then that brings additional benefits from the XLA project, where we can JIT compile it, just-in-time compile it, which means we can take the Python code that we can differentiate and compile it to process, like we can compile it to process it much quicker than we can do like basic Python. And then we can also, from the XLA project again, move it to GPUs or Google TPUs and just basically process it in parallel. Discussing these benefits of JAX might be a little bit boring. So first, are there any questions? Yes.
What about like JAX versus PyTorch?
JAX versus PyTorch or TensorFlow. So against like modern versions, well, JAX was developed with XLA, but the thing is that modern versions of PyTorch and TensorFlow both use XLA as a backend, so there isn't much a difference there. The main differentiator for JAX now is that you can just use plain Python to encode it, whereas PyTorch and TensorFlow generally have higher level. They're more meant to like build networks rather than code individual like functions that you might use. Yes.
What would be an example of a pure function?
A pure function, f of x is x squared. That's like most mathematical functions that you think of when you think of function are pure functions. They don't have side effects. They don't do anything outside of the function. Yeah. Any more questions? Anybody in the room have questions? No?
The whole
Yeah.
Python JAX JAX setup,
Yeah.
doesn't it mainly just help the compiling time being reduced? Because I understand even lists.
The
Yeah,
what
does
did
it just like make compiling time faster or also the running?
are you saying for
For the
Python and JAX?
versus just vanilla?
Oh, versus okay, so Python and JAX versus vanilla Python doesn't make compilation faster. No. It actually makes because Python doesn't need to be compiled. Well, it can be compiled with like JIT compiling, but it doesn't make the Python compiling itself faster. It makes the execution when you eventually compile. Like once you JIT compile it with XLA, you can execute it on a CPU maybe faster, but generally it's like XLA itself as a compiler is specialized to compile stuff for GPUs. So it would make it possible to compile Python on a GPU, like for a GPU, not on a GPU, and it lets you like execute it faster because maybe for CPU JAX and Python JAX. I mean, not Python JAX, vanilla Python JIT compiled. I'm not sure of like the differences there, but I'm pretty sure that a neural network running on vanilla Python JIT is much slower than a JAX compiled neural network running on a GPU or a TPU because it can take advantage of the fact that GPUs and TPUs have a parallel structure at its like most basic level. Yeah. Yes.
What's the difference between GPU and
It's a marketing term, I think. It's just like, oh, what's the difference between GPUs and TPUs? I think, to be honest, it's just Google sells TPUs, and maybe they have more cores than GPUs, so they can run faster for machine. Because for machine learning, you're trying to just like you want as many cores as you want, whereas GPUs you might still be balancing like cores with core speed. But with you do want like speed in a TPU, but it's not as important as the amount, right? Yeah. Okay. Any more questions? No. Okay. So let's look at a simple application that uses JAX. Let's see. So I have this web page. So we can look at this web page. This has a let me close this. This has a HTML canvas that you can click around, create points, and then we have a little number at the bottom left, at the bottom right corner, and that indicates the degree of a polynomial that we use to linear regress this the points. So what is a degree? The degree is just the highest power of a polynomial for a variable in a pure function, in a like equation. So like, for example, in a cubic function, the degree would be 3 because that would be the highest power. Or in a quadratic function, it'd be 2, and then so on and so forth. So if we look here, we can do this. And we have a line. And then we can just increase this, and it'll take a while because as I'll go into, we are using gradient descent, and generally one of the caveats of machine learning algorithms is that they're kind of slow, and this is executing on my CPU, so it's just not great all around. So as you can see, we now have a quadratic equation that is trying to fit these points, and we can increase it once more, and then we'll get a cubic function that is trying to fit these points. So we can look at let's look at the code to actually see, well, what's going on. So if we look here, so this is mostly just like HTML stuff, but the important parts are here. So we have our prediction function, which just basically evaluates some inputs with some weights. It just dots them together to see, or the input here is just, I'll explain what the actual inputs are, but it's basically just how to evaluate this, the linear function with respect to certain weights and see if what y does this set of weights and this single value of x produce. The reason why it's inputs is that we evaluate x for every power that's in the we evaluate x for every power that's in the equation. So if we have a degree 3, we need to evaluate x at power 0, power 1, power 2, and power 3. And if it's 6, we need to 0, 1, 2, 3, 4, 5, and 6. And that's what this loss function over here does. It takes the x, takes the y, it creates the input array, and then it dots it, predicts using it, and then it predicts using it, and then what we're using in this particular example is squared loss, which is we're just taking the y, we're taking the predicted y, subtracting the actual y that you clicked, and then squaring that. Because in general, loss functions, the value of a loss function should be positive or 0 so that we can try to minimize the loss, generally speaking. And then this is just like more connector code to like allow us to query this model, and it will train the model and respond, which is why it's so slow, is because it does need to train the model before it responds. So a way that we could make this faster would be to have a pre-trained model, but for this particular problem, that wouldn't really work because the user is providing the points that we need to connect, essentially. So we can't really pre-train a model for that. Another way would have been to parallelize the evaluation of the loss function. How to do that would be an exercise for the user, because I believe it was sent out in the invite, the repository that all this code is in. So you can actually download this code, try it out yourself, and see how to make it faster yourself. And another interesting caveat about this is that as you increase, like this fits pretty well. But if you were to increase the number of points and increase the power, it would not fit as well. The reason for that is that we trade off accuracy for time. We basically say we only are doing, like, I believe 100,000 iterations of this training loop. And if it takes over 100,000 iterations, we just return what we have. So that would be that would lead to like not so accurate results as you increase the degree that you're trying to evaluate at. So another interesting thing would be removing that limitation and seeing how long it takes, or trying to change that limitation. And another thing is with gradient descent, because we have just different degrees, the thing about gradient descent is you do have to have a step size, which is when you're evaluating the gradient, how far do you take that evaluation when you're trying to learn from it? We use a relatively small step size so that we don't, basically don't break the gradient descent algorithm, but experimenting with that step size and changing it to see yourself how it works would be an interesting exercise. Are there any questions about this code or the demo? Yes.
JMP.
JMP is the immutable NumPy that I talked about earlier. It is NumPy, but you can't mutate it in place. That's all that JMP is. And then go.
I guess, could you say like how you modify that? Like, how this is different from like a regular Python program? Like, how do you Jaxify it?
How do I Jaxify it? So how this is different from a general Python program is that it's not. It looks like a Python program, and that's the point of JAX. Like, you can take Python functions and just differentiate them and use them in your model. How it's different from other libraries is that generally in other libraries, you'd have an object that you would build that would be your model, and then you'd have a training step, and you'd call the training step on that object generally. So like, for example, PyTorch would have like a fully connected module, and or it's called a linear model or linear module, and you'd maybe connect a linear module to like an output module, and you'd use that to like create your network. It's not very direct, but that's like the benefit of JAX, is that it looks like Python, and it is basic Python, right? But yeah.
At some point, there must be a place where you just say differentiate this.
That is right, or that is right. Oh, I didn't actually, wow. That is right here, where it says value and grad. It outputs the value of the function, and then the differentiation of that function with respect to a certain variable that you input to that function, with respect to the certain variable that you input to that function. So yeah, that is that's why we use JAX, is that it's not an entirely like different paradigm, right? You don't have to use objects. You can just use functions and connect functions to each other.
And value and grad, is that a JAX function?
Value and grad is a JAX function. I do, because at the top I import it. If we go to the top, I import it here. It's a JAX function. Are there any more questions? Yes.
In this model, is like the step size static?
Yes, in this model, it's static. You can try like making it dynamic and see how it works. Yeah.
Why do you get that for a bunch of things?
Whether I get the dot product. So this is we're trying to evaluate like what the value of this function is with respect to certain weights, and you can evaluate a linear function, I believe, by like dotting like the coefficients of that function with the value of like the variables at that point in time, and then getting the output. So that's why we dot it. Yeah. Question? Yes.
So the function that you're making differentiable with plus, it says acchit, which is just the name, right? That doesn't affect whether it's differentiable, right?
Okay, so the @JIT decorator on top of the loss function, does that affect if it's differentiable or not? No, it does not affect if it's differentiable or not. That is one of the benefits of JAX, is that you can write plain Python, you can decorate it, make it a JIT function to be executed on CPUs, GPUs, TPUs, and then you still have your differentiation, right? So, yeah. Questions? Yes.
What is the advantage of JIT?
What is the advantage of JIT? This is actually a pretty bad example to show the benefits of JIT, but if you were to do a very complicated module or a very complicated model, and you're basically querying it many times. If you JIT it and you just compile it once, you can actually just make it execute much faster when you're querying it a bunch of times, because it doesn't have to rely on the Python stack and do Python things. It can just run on like bare metal because it is compiled machine code, or well, like GPU code, but like yeah. Question.
Are there any reasons you wouldn't JIT things?
Are there any reasons that you wouldn't want to JIT things? The JAX site does mention a few, but if you're relying on like some specifics of how NumPy works on a CPU, or because you do have immutable NumPy, so like some of the differences in how there are differences between how the compiled JIT function works and how it would work if it was just executing in NumPy. For example, if you were to take the I believe the exponent of a logarithm of 100 on CPU or on like non-JIT NumPy, that would be infinity. But on JIT NumPy, sorry, it would be 100, because when you're JITting it, because it's an optimizing compiler. Sorry, I forgot to mention that. It is an optimizing compiler, so it tries to make the code as efficient as possible, and part of that efficiency is avoiding calls when you can. So and especially it's in the context of linear algebra. So if you know that you're taking the logarithm of an exponent or the exponent of a logarithm, you can just replace it with an identity. So in the JIT function, it replaces it with an identity, so it can evaluate more values. But in Python, it would overflow on I believe the logarithm, and then, it'd overflow on the exponent, and then the logarithm would fail to evaluate infinity, I believe, I think I flipped the two, but yeah. Are there any more questions? Let me check the chat. Oh, there are. Okay, yeah. Are there any more questions? No? Yes? Okay. So let's look at the answer. These are the answers from last time, from Phoebe's lecture on DSP. I'll just leave this up for a few, some time. Let's talk through them. Okay, so if somebody's whistling at 16 kilohertz and you're recording them at a sampling rate of 20 kilohertz, what frequencies could the 16 kilohertz signal appear as? So if you look at the definition of the aliasing frequencies, you can look at it could be represented as a 4 kilohertz signal instead of a 16 kilohertz signal if you're sampling at 20 kilohertz. So then what sampling rate would you need to make sure that the 16 kilohertz frequencies are captured exactly as is with no aliasing? According to Nyquist's theorem, it'd be 2 times that frequency that you want to capture. So it'd be at least 32 kilohertz that you need to sample at to capture that. And construct the following for the signal: y equals x plus h equals 3x plus 5x n minus 1, where xn is the input signal and hn is the transfer function of a filter. And this is the signal in, I believe, the time domain, and this is the signal in the frequency domain. Yeah. So then we have some exercises for this time. These are mostly questions that are about exploring the documentation of JAX. So how do you handle randomness in JAX? Because generally randomness does need, pseudo-randomness needs a mutable state. JAX, you don't have mutable state. So how do you handle that? Why would JAX not support JIT compiling side effects and passing in arguments to create values based around? I did mention why it wouldn't do side effects. So you have half of this. And what are flags and alt tags? And where would we use them in our example application? These are just libraries that are essentially like JAX replacements of other libraries. And we could use them in certain places in the application, but I'm not going to mention which because that's the question. Are there any questions about these questions? No? Let me check the chat here. Or I gotta check it. All right. Thank you so much for listening to me speak.